Welcome to the third installment of Unit 2 in IB Physics. We're calling this Thermal Physics, and this is our third notes video. Okay, we already know that substances like liquids, gases, and solids are made up of molecules, which we draw with dots. We also know that each individual molecule has potential energy. So this one has PE, this one has PE, they all have PE. And the potential energy exists because of the attractive forces between molecules. Another thing we know is that they're all moving. Every molecule of any substance, liquid, solid, or gas, is moving. And so each of these also has, in addition, some small amount of kinetic energy, just like each one has a small amount of potential energy. If we add up all of the potential energy from all the molecules, and we add to it all of the total kinetic energy of all the molecules, then what we get is something called internal energy. Just one big number of the total energy of all of the molecules of the substance. That's what internal energy is. We'll see a formal definition in a little bit. Now, as it turns out, there are two different ways to change a substance's internal energy. The first that we'll look at is work. And the second that we'll look at is heat exchange. And we're also going to call this thermal energy. So already you see we will have thermal energy, which is different from internal energy, and we're also going to be using this other concept, work. The two ways, work and heat exchange, these two ways of changing internal energy, they are fundamentally different from each other. Let's get started on work. Work, you may recall, is a force acting over a distance. Well, actually, it's the product of force and distance. And there's this other thing we multiply by, cosine of theta, where theta is the angle between the force and the distance. Now let's assume that wherever the force is pushing, so if the force is pushing on something to the right, what we're going to assume is that the object moves in the same direction. So that theta, the angle between the two, is 0. And of course, if theta is 0, cosine of 0 we know is 1, and this becomes 1, so we could actually ignore it altogether in the simple case where the force and distance are in the same direction. And that's what we're going to do. Right now, we're just going to consider the simple case where theta is 0. So before we consider anything else, first, imagine a tennis ball and a tennis racket. The racket is here, and it's stationary. Perfectly drawn tennis racket. And the tennis ball is flying at it. So what happens? The tennis ball collides, and it bounces off in the other direction, assuming we hold the racket stationary. Okay. But what happens instead if you swing the racket during the collision? Well, in that case, the ball collides, and you are exerting a force. You're pushing with a force over some distance because you swing this thing forward, and so your force is applied over a distance. And as a result of your force, the ball goes flying off way faster than it would have normally. In other words, the ball gains kinetic energy when you swing at it. And Another way to say this is the ball gains kinetic energy due to the work that you've done. So the work produces a change in kinetic energy. In fact, not only can work produce a change in kinetic energy, work can produce a change in potential energy. For example, if you take a ball sitting on the ground, now the tennis ball is on the ground, and you lift it up, you exert a force on the ball over some distance, so you push the ball with a force over a distance. The work that you've done has just elevated the ball, and now it has potential energy. So work can produce two kinds of energy change, a change in kinetic energy and a change in potential energy. So we just write work equals the change in energy produced. Okay, now we're going to get back to the situation that we get back to our topic. We're going to look at a gas, a substance with internal energy. Okay, so we're gonna just take gas as the example of our substance, and what I'm drawing in now is a sealed chamber with a gas inside, and right here, this is called a piston. A piston is basically like a cylinder, so we're looking at it from a cross section, so it's actually kind of a cylindrical thing, and think of it as just a thick wall that can slide into and out of a chamber. So I've represented the gas inside the chamber with dots. And if you want to move the piston in, if you want to slide it in, you have to exert a force against it. And the reason you have to exert a force against it is the same reason you have to exert a force when you push your hand through water. Pushing the piston forward requires that you push out of the way and push against these little particles which are pushing back. Alright then, you put your hand on the piston, and you exert a force causing the piston to slide in so that a little bit later it looks like this. Right? And now you have exerted a force over a distance, and you have done work. And the work you've done is work that you've done on the gas. But when you applied the force and you did the work, what happened to the gas molecules? Well, when the gas molecules were colliding with this moving piston, they got hit by that force that you exerted. Just like the tennis ball got hit by the racket when you pushed the tennis racket forward. So as a result, they didn't just bounce off with their normal velocity, they were bouncing off with much higher velocity. So the gas gains kinetic energy when work is done on it like this. The gas gains kinetic energy. And the kinetic energy that the gas has gained is equal to the work you've done. So what have we learned? Well, kinetic energy, remember, is one of the types of internal energy, one of the things that makes up internal energy, rather. So doing positive work on a gas increases the internal energy. And it's not just true for a gas, this is true for any substance. It can be a solid, a liquid, or a gas. Doing work on a substance increases the internal energy of the substance. Now, there's a second way this could happen, right? There's a second way this could happen. Consider instead that the piston starts like, let's get rid of this. Consider instead that the piston starts like this, and instead of the piston sliding in, what happens? We let the gas push it farther out. So now the gas expands, pushes that piston out, And as it pushes out, that gas is pushing against outside air on the outside of the piston. Okay. So that gas on the inside has to exert a force. It's exerting a force to push the other air, the outside air, out of the way. And the force acts over some distance. So when this happens, the gas is exerting the force. And in this case, what's the effect produced on the gas inside of the piston, inside of the chamber? What's the effect on this gas? Well, what's happening is the gas particles are colliding, they're exerting a force, and when they collide and exert a force, when they bounce off, they're losing some of their kinetic energy because they're giving it to the piston, and the piston is then colliding with these outside air particles, causing them to bounce off faster. So the kinetic energy is being transferred from the inside gas to the outside air. And when that happens, the particles are losing their kinetic energy. So what have we learned? When a substance, like a gas, does positive work, the substance's its internal energy, in this case Ke decreased, but it could be potential energy as well. The substance's internal energy decreases. So those are the two things that we've learned. When the substance does positive work, it loses some of its internal energy, and when positive work is done on it, it gains some internal energy. Notice that in this case, both cases we saw, we have been dealing with the application of a macroscopic force. Something is getting pushed, right? This piston is getting pushed with a force. Or on the other hand, you could be pushing the piston with a force. There is a second way for a substance to gain or lose internal energy, and it's called heat exchange. This is different from work. Okay, let's say we have a cup of water. Water is blue, and the temperature of the water is 30 degrees Celsius. If you take an ice cube and you put it inside, and let's say the ice cube is at 0 degrees Celsius, what's going to happen? The ice cube is going to melt and get hotter, turn into hotter water than 0, and the surrounding water, which is at 30 degrees, will get a little bit cooler when it mixes and interacts with this colder cube. So the ice cube gains temperature, which means that its molecules will gain kinetic energy, and hence they'll gain internal energy. So just by sitting there, just by being in what we call thermal contact, internal energy, or the internal energy of the ice cube increases. That ice cube gains internal energy. Its molecules become faster moving. And this is an example of something happening, internal energy increasing, without any macroscopic forces. So we call this kind of energy transfer without any macroscopic forces, we call it non-mechanical. That's what it means, and what this means is no macroscopic forces. It's different fundamentally from what's happening when you do work on a gas. So what's happening here? how is this energy being transferred from the water to the ice cube? The answer, you may know, is something called heat. Heat, or in IB physics, the term we use for heat is thermal energy. Heat, thermal energy, is exchanged. And how does it go? It's exchanged from the hotter object, the water in this case, to the colder object. I'm craving a glass of ice water right now. Okay, so how does this kind of thermal exchange, this exchange of thermal energy, how does it actually work? Well, there is something cool here. So zoom in, let's imagine we zoom in on like one side of the ice cube. It has these solid particles which are really tight, packed together. They are vibrating. Their kinetic energy is mostly just vibration. And they're not moving very fast because their temperature is 0, so they don't have a lot of Ke. We'll say each has a small Ke because they're not at a very high temperature. On the other hand, they are being bombarded by these faster moving liquid molecules which have bigger Ke, so I'm going to make Ke bigger. How do I know the Ke is bigger for the liquid? Because the liquid is at 30 degrees, it's hotter, and so its molecules have greater kinetic energy. And so when these bigger Ke molecules bump into the small Ke molecules, they transfer some of their Ke to the solid, and then they start moving back and forth. Eventually, they get going fast enough to break free, and the collisions continue until everything is at about the same temperature, or everything is at exactly the same temperature. So this process is the process, what's happening at the smaller, the microscopic level. This is the process by which the by which the internal energy of the ice cube increases. That's how this happens. Now you may be wondering, what's the difference between internal energy and thermal energy, right? Because what thermal energy is just the heat that is exchanged. Internal energy is the heat that the molecules possess. So in IB physics, there's a really important distinction between these two concepts. Here's the distinction. Internal energy is the energy the molecules possess. On the other hand, thermal energy is the energy the molecules, or let's say not molecules, excuse me, the energy the substances transfer or exchange. In other words, it would be wrong to talk about the thermal energy inside of a substance. Thermal energy only refers to the energy that's being exchanged. So you don't say substances have thermal energy, you say that they exchange thermal energy. And likewise, once that thermal energy has been exchanged, we stop referring to it as thermal energy and we start talking about it again as internal energy. So thermal energy is simply the change in the internal energy produced by the heat exchange. Thermal energy is just how much internal energy does the ice cube gain. That's how much by this heat exchange process. That's what the thermal energy is. It's how much the internal energy increases. Okay, let's summarize what we have learned. We know that an individual molecule has PE, potential energy, and kinetic energy. There's this new term, internal energy. It is the sum of the total PE and total kinetic energy of all the molecules of a substance. Another thing, there are two ways to change the internal energy of a substance. One is with work, and the other is through thermal energy, or we could say heat exchange. Work, what is that? What is work? Work is the mechanical transfer of energy via a macroscopic force. And on the other hand, thermal energy is the energy, this is kind of a definition of thermal energy, the energy exchanged non-mechanically between substances that are in thermal contact. That's a pretty good definition of thermal energy. Oh, that are in thermal contact and that are at different temperatures. And that's a pretty good definition of thermal energy.